In this mini lecture, we're going to talk about graphing quadratic functions. And let me remind you of what a quadratic function is. A quadratic function, we have one named ff. It would be f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers, and specifically a can't be 0, otherwise we wouldn't have an x squared. So there's certainly different examples of quadratic functions. One example, let's see here. What do I want to try? Well, as you can see, I've paused and listed several or three different quadratic functions. But in each of these quadratic functions, we actually have three terms. But quadratic functions might not have all three terms. For instance, we might have y is equal to x squared minus 2, or y is equal to x squared plus 3x. So we don't have to have all, and as far as that goes, we could just have y equals x squared. What we do have to have is the x squared term. Otherwise, it's not a quadratic function. And there are several things about these quadratic functions that we want to know about. And one is how to find the vertex. Oh. Okay. We want to know how to do that. And let me remind you that quadratic functions have graphs that are parabolas. So what we know is that our graphs are going to look something like this. Now, a parabola can be of that form, or it can open downward instead of upward, or it can be open wide, or it can open in a very skinny way, okay, a very narrow way. Those are all different ways that a quadratic function can look. And of course, remember, this position that's kind of in the middle is either at a low position or a high position. Here's a low position, here's a high position. That point, of course, is called the vertex. So that's what I mean about how do we find the vertex. Now, if you draw a vertical line through that vertex, like I've done here, that vertical line is called the axis of symmetry. Sometimes it's just called axis. Sometimes it's called axis of symmetry. It just depends on the book you're reading or the material you're reading. And the idea behind that axis of symmetry is that if you fold the graph along that axis of symmetry, the two sides of the parabola match. And so it kind of gives us an idea that if we were trying to sketch a graph, we could get points on one side, and there would be matching points on the other side, which would make it easier for us to make a graph pretty rapidly. Of course, that axis of symmetry is a vertical line, and it goes through the vertex. And vertical lines are written as x is equal to. We'll come back and see that. And notice also, as I mentioned earlier, it's important to know whether a graph, whether the parabola is going to open up or down. So how do we determine if the parabola or if the graph opens up or down? And that's probably the easiest thing to determine if you recall. Okay, and we'll go over that here in a moment. What else might we like to know? How to find intercepts. In general, we need to know how to find intercepts, and there's two classifications of intercepts. There are x-intercepts, and there are y-intercepts. Okay, now in the case of a y-intercept, and we're graphing a function, we can only have one. And in the case specifically of quadratic functions, there's exactly one. And the idea behind that, of course, is this parabola opens, the two edges keep widening. It spreads out. And if it spreads out, eventually it's got to cross the y-axis. And no telling where it crosses the y-axis, but if it continues to widen, then it, of course, takes up every kind of x value that we can get. It goes across the whole spectrum of that x-axis eventually. So every quadratic function has one y-intercept exactly. Now for x-intercepts, though, that's a little bit different. There might be none. There might be one, or there might be two. And just kind of a quick thought on that idea, let's just look at a coordinate axis situation here. See, if this is what our xy axis looked like, and we had a vertex that was here, and the graph, the parabola opened up, then that graph is never going to cross the x-axis, is it? Eventually it will cross the y-axis somewhere way up there, but it will never cross the x-axis. So this is no x-intercept in this case. So what would be nice to know here, it would be silly to look for an x-intercept if we know there's not one. And to know that, then we could say, well, if we know what where the vertex is, and then we know that the graph opens up or down appropriately, we can look at we can decide whether it has an x-intercept. And here's again what I mean by that. See, in this case, let's suppose our vertex is in the same place, but this time we know that the parabola opens down. Well, in this case, of course, then there are two x-intercepts. It crosses the x-axis in two different places. So there's a situation where we have two x-intercepts. Now, another kind of thing that can happen is if the vertex itself is exactly on the x-axis. There's the vertex, and let's say the parabola opens up or down, it really doesn't matter. Since the vertex is on the x-intercept, it doesn't cross the axis, it just touches it. So here's an example of one x-intercept, and we can have any of those situations. We just have to be prepared. But if we know where the vertex is, and we know whether the graph opens up or down, we'll be able to tell how many x-intercepts it has, so we'll know whether to look for those x-intercepts rather than wasting our time. Okay. Let me remind you then, that's the idea about finding x-intercepts, but remember, how do we find an x-intercept? I'm kind of working, well, I apologize. Let me go back up here to how to find the vertex. And again, I'm not trying to teach you this from scratch. In an earlier algebra class or a pre-calculus class or something like that, you saw how to do this, and a great deal of time was spent on developing it. Right now, we're just refreshing that old information. Now, let's assume that the vertex, okay, we're going to call by the coordinates just for us to refer to something h comma k. So h is the x value of the vertex. And to find the vertex, we have what's called the vertex formula. And the vertex formula doesn't tell us the vertex, it tells us the x value of the vertex. It tells us that this h value is opposite of b over 2a, where b is what we're talking about way up here. It's the coordinate of the x coordinate, and the coefficient, pardon me, and a is the coefficient of the x squared term. I should have said b is the coefficient of the x to the first power term, and a is the coefficient of the x to the second power term. So that's the way we can come up with the x value of the vertex. Well, then how do we find out what k is? Well, what we end up doing is that we put the known x value in, okay, that would be what we just calculated above. We would put that number into the function. In fact, that's how we find y values, isn't it? We take the given x value or the known x value and we put it into the function. So we use a formula to calculate the h value, and then we just use the equation to calculate the y value once we know the x value. So that's pretty quick for us to do that. Now, if you also recall, there is an easy way to determine whether the graph opens up or down. And it depends on the leading coefficient a. And what it boils down to is that if the a value, that's the coefficient of x squared, is greater than 0, then it opens up. If the a value is less than 0, so a value being greater than 0 means it's positive, doesn't it? And a value being less than 0 means a is negative. And in that case, it opens down. You saw that when you talked about transformations of functions. So you can look up at this graph, at this function, and the a value is 1. It's f of x is equal to 1x squared, except we just don't say the 1. And so this opens up, doesn't it? In this example, we can look at that and say, okay, the a value is -3. And so we know that that opens down. Well, that's easy. That's the easiest thing we've done, period, isn't it? And of course, we can see the third one opens down, and the fourth one opens up, and the fifth one opens up. And we can tell that just by the form of the function. Okay, now, it's not going to be difficult for us to find, furthermore, the vertex of any of those, and it's not going to be difficult for us to then decide how many x-intercepts it has, and we need to be able to find those x-intercepts. So let's pause this. We'll go to the next page, and we'll be going through the idea of graphing at least one or some of these functions. Okay, here we're going to graph the function f of x equal x squared plus 4x plus 6. In fact, if we have homework, it might say analyze and graph. So let's begin gathering some information before we plot any points. And we'll just make a note here that we see that the graph opens up, doesn't it? We know it opens up because the coefficient of x squared is 1, which is positive. It opens up, and that was because the a value, which we recognize as 1, is greater than 0. Okay, well, let's go about finding the vertex now. And remember, a lot of times we'll refer to it h comma k, but it's really just the x and y value of the vertex. And what we saw a couple of minutes ago is that we can calculate that x value of the vertex by saying the opposite of b over 2a. Now, in this case, the b is the 4 value, which is the coefficient in front of x to the first. So we have the opposite of b, the opposite of 4, over 2 times a, and since a is 1, that would be 2 times 1. And you can see that's -4 over 2, which is -2. So our vertex has an x value of -2. Now, once we know the x value, we're needing to calculate the k value, which is nothing more than y, isn't it? And the way we calculate the y values is that we put a x value into the function. And the x value, of course, that we need is -2. So we simply put -2 into the function. And so we replace each x with a -2 in the function. And then we do our calculations. Well, this becomes a +4 here, a -8, and a +6. And that ends up being +2. So the k, or the y value of the vertex, is +2. So now we know where the vertex is. It's -2 comma +2, which would be this position right here. Now, and we know that the graph opens up, don't we? See, here's kind of the information we have. We've got a vertex out here someplace, and from the fact that it opens up, what we know now is there is no x-intercept. So we don't need to try to find one, do we? No x-intercept. But it always has a y-intercept. So that's the next thing we need to do. And if you recall, the way we find y-intercepts, and just in general, okay, now not specific to this, but when we've got a graph that crosses the y-axis someplace, wherever it is, what we know about that point where it crosses the y-axis, that point has a value of 0 for x. It's the y that we don't know. And so what we need to make sure of then, for a y-intercept, we've got an x value of 0. So we let x be 0 for the function, and we go about and find the y that we get when we know x is 0. So that's a matter real simply here to say y is equal to f of 0. That is, again, we just put 0 into the function in place of x. So we have 0 squared plus 4 times 0 plus 6, which is just, of course, 6. So that tells us the point 0, 6. The x-coordinate 0, the y-coordinate 6, 0, 6 is the y-intercept. And that's this point right here that I'm sketching in. Okay. Now, that actually, let's stop and think what else we might want to know. Oh, we may be asked for the equation of the axis. The equation of the axis, or the axis of symmetry. If we're just doing a real quick sketch here, the first thing we've got to remember is that the axis of symmetry is the vertical line that goes through the vertex. And this negative 2, 2 is where the vertex is. So we imagine the negative line, the vertical line that goes through that. Now I'm putting it in as a dashed line because that's not really part of our graph. So it's that vertical line that's the axis of symmetry. And remember, vertical lines have equations that say x equal. And so in this case, it's x equal negative 2 is that vertical line. Now the significance there, here's really the reason I'm mostly worried about that. We have this point that is up here that we know is on the graph of the parabola. And because of the symmetry, there's got to be one on the other side of that axis that lines up with that. And if you'll notice, this point 0, 6 is 2 units horizontally, 2 units to the right of the axis. So if I move 2 units to the left, that would be right here. And of course, that point's negative 4, 6, isn't it? It's just 2 units in the other direction. That will be another point on the graph. And with those 3 points, I can do a reasonable sketch of the graph. And that's all I'm really worried about here. So now, knowing that this is the vertex down here, then, of course, as I draw or sketch this in, I have some idea of what that graph looks like without a great deal of trouble. Okay, well, let's, on the next page, let's look at one that has a few more issues, but now that we kind of have a feeling for how to do this, maybe we can move more quickly. Okay, you can see here we're asked to graph y equal negative 3x squared minus 2x plus 1. And I've already got a coordinate axis set up, and you see I've scaled it a little differently, and it's not quite fair to you. I happen to have a pretty good idea of what this graph is going to look like ahead of time. And so I knew I could scale a particular way ahead of time. And you're not faced with that, obviously. But let's go kind of down the line real quickly. We can see that this opens down in this case, can't we? Okay, because our a value is negative 3, and that's less than 0. And whenever our a value is less than 0, or a negative number, then we know it opens down. Now, to find the vertex then we're going to find first the x value, h, and then we're going to use that x value to find the k value. And to find the x value, we use what's called the vertex formula, which says it's the opposite of b over 2a. And in this case, b is the number -2. It's the coefficient of x. And in this case, a is the number -3, the coefficient of a squared. And you can see this ends up being a +2 over a -6. Which ends up being a -1/3. So we have a little more issue here, don't we? We've got some fractions involved. Okay, so that's the that we know that the vertex has an x value of -1/3. Well, what's the y value? Well, the y value is k, isn't it? And the way we find that y value is we put, that's just the y value, and the way we find that is we put our known x value into the equation. So in place of x, we'll put a -1/3, and so it'll start out as -3 times the -1/3 squared, and minus 2 times x, but of course x is -1/3, and then finally plus 1. And so as we go back and look at this, let's see here, when we square -1/3, we'll get a +1/9. I mean, obviously, negative times negative is positive, and 1/3 times 1/3, we multiply the 1s together on top, the 3 together on bottom, leaving 1/9. Next, we have a negative times a negative, which is positive, and we have 2 times 1/3, which is 2 over 3, and then plus 1. And then we look here and say, okay, -3 times 1/9 is -3 over 9, which is -1/3. And I'm assuming that you can do this work. I'm just speeding things along. And of course, -1/3 plus 2/3 is 1/3. So we have 1/3 plus 1, which is 4/3. And that's the way we would write it. But we might, when we're graphing, want to recognize that that is 1 1/3. So the y value of the vertex way back up here is -1/3, 4/3. So if we go and plot that, an x value of -1/3 would be roughly in here, wouldn't it? And a y value of 4/3, which is 1 1/3, that would be roughly up here. So our vertex is roughly where I've sketched it in there. Now we know this graph opens down. So if we have a vertex that's here and our parabola opens down, then we certainly have two x-intercepts. And so that's what we're going to go about finding now. We know that it has two. Well, how do you find x-intercepts? Well, more generally, once again, just as a reminder, if you have a graph, no matter what it's the graph of, that is going across the x-axis, those points, we don't know the x value of those points, but since it's on the x-axis, the y value is 0. So what we always do to find an x-intercept is that we know the y value is 0, and we've got to find the appropriate x's. In other words, the x's that cause the y value to be 0. So in this case, we go back to our original equation, y equal -3x squared minus 2x plus 1, and we know the y value is 0, and so what we're needing to do is find the x's that cause that y to be 0. And that is always about solving an equation. And that's the reason finding x-intercepts is more tedious, because we have to solve this equation. Well, this is a quadratic equation, so we've kind of practiced at that. Now, because this starts with a negative, what we might do is factor out a -1, and that would make it easier for us to factor in a moment. So I'm going to factor out a negative, or -1, and rewrite that as positive 3x squared plus 2x minus 1. That just makes our work a little easier. And in fact, if I think of that as a -1, if I divide on both sides by that -1, it will make my job easier yet to solve the equation. Oops, that's the 3x squared. I'm sorry about that. plus a 2x minus a 1, and I'm dividing by negative 1. So those go out, and that's just 0. So it actually makes my job quite a bit simpler to worry about solving that equation. Now, if I can factor this, I can solve by factoring. If I can't factor, then what I would do is use the quadratic formula. And if I use the quadratic formula, I might get an answer that involves square roots. And then I would have to approximate it so that in those cases, I might get some kind of decimal answer as an approximation. But in this case, I think that we can actually factor. So let's see. And I'm assuming it's going to have to be a 3x times an x, obviously. And I'm thinking what we need, let's see, how about a plus 1 here and a minus 1 there? Doesn't that do it? That gives us negative 1 at the end, 3x squared at the beginning. It gives us a 3x and a minus x for the middle, and that, of course, is 2x. And so now we take each of those factors, 3x minus 1 being one of them, set it to 0, and the other one being x plus 1, and set it to 0, and then solve. Well, in this case, we add 1 to both sides and divide by 3, so I'm just kind of scooting along here. I know you could do it. In this case, we'll subtract 1 on both sides, and so we actually have two x-intercepts. Now, one of them has an x value of 1/3, but of course y is 0, and in the other one, we have an x value of negative 1, and of course the y is 0. So we ought to be able to plot those points. Let's see, 1/3 comma 0 we'll say is roughly here. And negative 1 comma 0 we know is here. Now I suppose we could do one more thing. And that one more thing is well, we may need to do two more things, but that one more thing that we would like to do is to find the y-intercept. And the y-intercept is always easy. Remember, we let x be equal to 0, and we find y. And you can look up at the equation. When you let x be equal to 0, you have y is equal to 0 plus 1, where you simply get y is equal to 1. And so the y-intercept is the point 0, comma 1. And as I go up here and plot 0, comma 1, that's the point we have right there. Now, because of the axis of symmetry, then I know I have a matching point on the other side of that axis, which we'll say is roughly about there. Okay, roughly there. And now we've got plenty of points to use to graph this with, don't we? So we know where the vertex is, and it opens down. And so we have something that looks like that. There's our graph. And of course, the axis is a vertical line, and the vertical lines are x equal, and it's the vertical line that goes through the vertex. And since the vertex has an x value of negative 1/3, it's x equal negative 1/3. Now, on the next page, I want to kind of speed up some special situations. So we'll go through that real quickly, but we'll do that on the next page. Okay, here you see that we're asked to graph y equal x squared minus 4. And of course, what's special about this one is that we don't have the term involving x. And you know, if we remember what the y equal x squared is like, and we should remember that would be a graph that looks like this, wouldn't it? Well, we should have learned in a previous algebra class about transformations, and that y equal x squared minus 4 looks like y equal x squared, except that minus 4 causes it to move down 4 units, doesn't it? So we ought to know that we've got to move that graph down 4 units, and so the vertex would be down here, and so now the graph looks something like that. Y equal x squared minus 4. Now we're going to go through a few steps, but I want you to have that anticipation so that it makes things like this much easier for us to graph. So we already know that it opens up. That's not any question, okay? We can tell that by looking. Now, when we go to find the vertex, this is what I want you to notice. The vertex is of the form h comma k. And remember, we use the vertex formula, which is h is equal to the opposite of b over 2a. And when we have a equation that doesn't have x to the first power in it, when our function doesn't have x to the first power in it, then the b is 0, isn't it? So we have minus 0 over 2a, and in this case, that's 2 times 1. But the fact that the numerator opposite of 0 is just 0, the fact that the numerator is 0 means the fraction is 0. Now, the significance there is just what we talked about earlier. What's happening here is if we don't have x to the first power term in there, the vertex has an x value of 0, which means the vertex is on the y-axis. And so the vertex is just moving up or down. And we can see real quickly here the way we would calculate k, which is just the y value, is we would put that 0 into the function. Well, 0 squared minus 4 is just negative 4. And so that's, as we just said a moment ago, it basically moved the graph down. So as a quick sketch, and I'm trying to save a little space here, as a quick sketch, since I kind of have an idea of what's going to happen here, here's of course the y-axis and the x-axis. Let's say there's negative 1, there's negative 2, there's negative 3, there's negative 4. And so down here where x is negative 4 is the new vertex, isn't it? Now, the only real issue that we have next, and we know it opens up, is that we've got to somehow decide what the x-intercepts are. That would be pretty easy. In fact, that'd give us enough points to be able to figure out what's going on. And so we already know that the y-intercept is 0, negative 4. That's where the vertex is, and it's on the y-axis. But for x-intercepts, remember we let y be equal to 0. And we solve for x. We find x. Well, if y is 0, we have an equation that says y is equal to x squared minus 4. And that's fairly easy for us to solve because this is that type of equation where we only have x squared and not x to the first term, pardon me. So what we end up doing here is that we add 4 to both sides and get 4 is equal to x squared. Well, let me write that as x squared is equal to 4. And so there are two solutions to that, positive and negative 2, right? So we have x-intercepts of negative 2 comma 0 and of positive 2 comma 0. Well, that's what this is supposed to represent. There's where x is negative 2, there's where x is positive 2, and so we can sketch this very quickly then, okay? Okay, a couple of real quick examples now, because that's what I'm after, is these things that are a little simpler. Example, we'll say example 4. And we're to graph y is equal to x squared plus 2. Well, what I want you to recognize there is that we're taking the y equal x squared and we're raising it or shifting it up 2 units, aren't we? So here's our coordinate axis. There's 1, there's 2. And if we shift it up 2 units, our vertex ends up being there, doesn't it? So our vertex is 0, comma 2. And if it opens upward, I'm not worried about a lot more than that. We already know it opens upward because A is positive 1, and so we don't have any x-intercepts, and our graph looks similar to that. Well, we could get a few more points if we wanted to. Now, let's finish this off by looking at something that this way. Let's say example 5, and we're to graph. I hope this isn't getting too sloppy. I don't get to see what the video looks like until much later. Let's say the opposite of x squared plus 3. Okay, well, a little difference we have here is that negative x squared, don't we? And so what we know here is that this one opens down. It opens down because a is -1, and that's less than 0. But we also know that it's going to be shifted up 3 units. Now, those two pieces of information give us a quick idea of what this graph looks like. So let's imagine there's 1, there's 2, there's 3, and of course there's 4. And we're shifting up 3 units and we're opening down. So it's going to go like that. Now, what are we going to do about the situation for finding the x-intercepts? Well, remember, to find x-intercepts, I'm trying to find space to do this. To find x-intercepts, what we have to do is let y be 0, and so we're looking at 0 is equal to -x squared plus 3. And when we look at that, if we add x squared to both sides, that becomes x squared is equal to positive 3. I just added x squared to both sides. And so x is plus or minus the square root of 3. Now, in this case, we'd probably need to get our calculator out so that we could decide that the square root of 3 is about 1.7. So we get x values of positive 1.7 and negative 1.7. So if this is where 1 is, this is where 2 is, here's -1 and -2, then 1.7 would be roughly here, -1.7 would be roughly here, and that information then is enough for us to determine what the graph looks like, and then we could answer the other questions specifically about what's the x-intercept, what's the y-intercept, what's the axis. And see here, the axis is x equals 0, isn't it? That's the line that goes through x equals 0. It happens to match the y-axis here. But of these forms, and later in this class, we're going to see that we need to be able to deal with these graphs rather rapidly. The graphs we looked at before take a little bit more time, and we need to expect that. This is all I want you to know for now about graphing quadratic functions.